Welcome back to the Deep Dive. Today, we are undertaking a very targeted mission tailored just for you. We know you're tackling one of the most critical subjects in modern engineering education, big data analytics.
That's so true.
Data isn't just stored anymore, it's engineered.
Yeah,
And knowing the foundations of that, well, that's the core skill.
that's absolutely right. And our goal today isn't just to, help you pass the exam. It's to give you the structured thinking you need to approach massive data problems in the real world. We are diving right into Module 1, Introduction to Big Data from your syllabus.
Okay.
We want to provide the clarity, the structure, and the essential engineering context to make this complex topic immediately accessible.
So what's our trajectory here? We're going to establish exactly what big data is, detail the characteristics that make it so challenging, the famous 5 Vs, and then map out the full architecture methods and the crucial analytics lifecycle required to extract genuine value.
Yeah, a logical path.
We're moving logically from definition all the way to solution.
Exactly. And when you're studying this module, it's so important to see that progression. We start by defining big data and establishing its fundamental differences from conventional data.
Okay.
That difference then forces a complete overhaul of the systems we use, which leads us right into the required infrastructure, architecture, and platforms. We then solidify the definition with the 5 Vs, and finally, we detail the action plan, the analytics processes, intelligent data analysis, and the crucial big data analytics lifecycle.
That systematic approach works perfectly. So let's start with that foundational moment. The name big data is almost, well, it's misleading because it implies size is the only factor.
It does.
What's the technical definition that goes beyond just, a lot of data?
That distinction is paramount for an engineer. Big data is defined as data sets that are so large, so rapidly generated, and so complex in their variety that traditional data processing software...
So like standard databases.
Exactly. Standard relational databases and tools designed to run on a single server, they're simply inadequate to manage or analyze them within a reasonable time frame. It's a crisis of scale, speed, and structure.
That immediately frames the essential comparison we need. And I'm guessing this is a guaranteed exam question. Conventional data versus big data.
Oh, absolutely.
How should we structure that contrast clearly?
Think of conventional data as primarily structured. It's clean, it's organized, and it fits neatly into predefined rows and columns, typically in an equal database.
Right.
It operates on a small to medium scale, processed sequentially by a single server, and it relies on a static schema, and that's a key term. A static schema means you have to define all your columns, your data types, your relationships, all up front before you put in the first piece of data.
And big data is pretty much the opposite in almost every respect.
Precisely. Big data is a mix. You have structured, semi-structured like JSON or XML, and then completely unstructured information. Images, raw text, sensor logs. It exists on a massive or infinite scale, requiring distributed processing, so using clusters running Hadoop or Spark across hundreds of machines. And critically, it operates with a dynamic or non-existent schema.
Wait, let's pause on that dynamic schema concept. What does that actually mean for an engineer who's building something?
It means we often prioritize ingestion over immediate organization. So instead of defining the structure first, we ingest the massive, messy data first. It's an approach called schema on read.
Schema on read.
Okay. The structure is often inferred later, or it changes constantly, and that allows us to incorporate new data types without bringing the entire system down for retooling. This flexibility is absolutely essential when you're dealing with variety and velocity.
That makes perfect sense. The scale and the structure dictate entirely new tools. Now let's move to the characteristics that define this whole environment, the famous Vs. These 5 points really explain why the old systems broke down.
They do. The 5 Vs of big data are really the definitive engineering constraints we have to solve.
Okay, let's begin with the constraint of scale. Volume.
Volume is the sheer size, and we're often measuring it in petabytes and zettabytes. The challenge isn't just storage, it's processing all of it.
Right.
A perfect practical example is the constant stream of raw sensor data generated by a major airline fleet. Every engine, every flap, every navigational system reports its status every single second. That volume forces us into distributed storage solutions.
Okay, so moving from scale to speed, next we have velocity.
Velocity is twofold. It's the speed at which data is generated and then the speed at which it must be consumed. Think of high-frequency stock training systems where latency tolerance is measured in milliseconds,
Wow.
or fraud detection, which has to operate instantly. This raises a crucial engineering choice: batch processing versus stream processing.
So how does that choice actually play out in practice?
Well, batch processing is the traditional way. You collect data over a period, you save it, and then you run a large scheduled analysis. It's high latency, high volume. Stream processing, which is necessary for high velocity, involves analyzing data the moment it's generated, often in memory before it's even stored. Low latency, infinite stream. Velocity often forces engineers to choose the complexity of stream processing.
Got it. Next up, the complexity of structure. Variety.
Variety refers to the heterogeneity of the data. We have to handle simple database entries right alongside unstructured data like customer service call transcripts, semi-structured web logs, GPS coordinates. The engineering challenge is integrating all of these disparate formats, normalizing them, and then making them usable for a single analytical model.
The fourth V is where the rubber meets the road in terms of decision-making. Veracity. This feels like maybe the most critical challenge for engineers building reliable systems.
It absolutely is. Veracity speaks to the quality, the accuracy, the trustworthiness of the data. Big data environments are just inherently noisy. Data can be biased, incomplete, or corrupted by faulty sensors. Imagine building a predictive maintenance model for a power plant based on an instrument that intermittently fails. If the input veracity is low, the prediction is useless, or even worse, it could lead to a catastrophic shutdown.
So a huge amount of time is spent just on cleaning.
An enormous amount of effort in pre-processing is dedicated just to improving veracity.
So we tackle all those four Vs, volume, velocity, variety, veracity, for one single reason, and that is value.
Value is the ultimate goal. It's the ability to translate all that effort and infrastructure investment into actionable insights, process optimization, efficiency gains, or, profit.
Right.
If the engineering effort doesn't lead to value, like a reliable predictive model, then the entire big data stack is just an expensive way to store noise.
So handling those five Vs requires a complete rethinking of how we build systems. We have to move the computation to the data, not the other way around. Let's expand on the architecture. What are the conceptual leaps we need to make to understand big data architecture?
The conceptual shift is really key. We are giving up the simplicity of a single powerful machine for the complexity of a massive network of commodity machines. Big data architecture relies entirely on distributed systems.
Okay.
We partition the data across hundreds or thousands of servers using designs often based on the master-slave concept. The architecture has to be modular, focusing on separate layers for storage, processing, and consumption.
But doesn't distributed processing inherently introduce complexity and network latency? What engineering trade-offs are we making to get that massive scale?
That's the core engineering dilemma right there.
Yeah.
We sacrifice the simplicity and the low latency you get in single-server processing for massive horizontal scalability.
Okay.
The architecture must be highly concerned with fault tolerance. Since you are using thousands of inexpensive machines, hardware failure isn't a possibility, it's a guarantee.
Right. Something is always failing.
Exactly. The system must be designed to detect failure, automatically replicate the missing data, and reassign the processing task without stopping the entire operation. That is the genius of platforms like Hadoop. They handle this complexity transparently for you.
Speaking of platforms, so we have the architecture and then we have the tools that run on it, the big data platforms.
Yes, platforms like Hadoop and Spark are the software frameworks built on that distributed architecture. They basically abstract away the complexity of managing thousands of servers and allow engineers to write code that automatically runs in parallel across the whole cluster. They're the engine.
Got it.
They're the engine that enables parallel processing across enormous data sets.
So once the infrastructure is set up, we need a plan to actually extract knowledge. Let's talk about the analytic processes and methods.
The overall process is very systematic. It follows the scientific method, just adapted for massive scale. We start with data acquisition, then the extensive step of cleaning and integration, followed by analysis using various methods, and finally concluding with visualization and reporting.
And the big data analytical method itself, how does that differ from, say, traditional business intelligence?
It's the strategy for solving the problem. Because the data has such high variety and high volume, the analytical method almost always involves sophisticated statistical modeling, data mining and machine learning techniques designed to find complex patterns.
Which leads us directly to intelligent data analysis, or ID.
Exactly.
How should an engineer define IDA?
IDA is the use of sophisticated computational methods. AI and machine learning are central here to automatically extract complex, non-obvious patterns from high-dimensionality data. And high-dimensionality just means you have a vast number of features describing each data point. IDA is that crucial bridge that allows us to find insights in the noise created by the 5 Vs.
Now we come to what you said is maybe the most important procedural sequence for both the real world and for the exams. Just a big data analytics lifecycle. Can you detail that step-by-step process that defines an entire project?
I can, and the sequence must be memorized and understood as a workflow. It typically has 6 main stages, and it always starts with context. Step 1, problem definition or business understanding. You have to clearly articulate the objective, the scope, the success metrics. What question are you actually trying to answer? Step 2, data acquisition and selection. This is identifying the relevant data sources, internal databases, external streams, social media feeds, and pulling that raw data into your distributed system. Step 3, data pre-processing. This is the unsung hero of the whole process. It often consumes 60 to 80% of the project time. It involves cleaning the data, handling missing values, transformation like converting text to numerical features, and addressing all those veracity issues we talked about. Step 4, data analysis and modeling. This is where you apply the actual algorithms, statistical models, clustering, machine learning, to build your predictive or descriptive model. Step 5, visualization and communication of results. This means translating the complex model output into understandable visualizations and reports for non-technical stakeholders. And finally, step 6, deployment and operationalization. This is where you take this successful model and you integrate it into the live system, whether that's an automated recommendation engine or a real-time fault prediction dashboard, and ensuring it continuously provides value.
That makes the process so tangible. So connecting this all back to engineering reality, where are these concepts applied today, and what should the listener really focus on for high marks?
The applications are everywhere, and that's what links the concepts to tangible systems. Think about the energy sector. Using sensor data, that's volume and velocity, from thousands of wind turbines combined with weather patterns variety to predict maintenance needs. That's the value. Or in healthcare, analyzing electronic health records combined with genomic data for personalized medicine. This is big data solving massive, complex problems.
And crucially, for the KTU exams, what are the absolute exam hotspots? What do they need to nail?
Okay, focus intensely on 3 areas. First, defining all 5 Vs with clear, separate, practical examples for each one.
Got it.
Second, mastering the detailed comparison between conventional data versus big data. I would recommend presenting that in a comparative table.
Good tip.
And third, listing, explaining, and understanding the workflow of the 6 steps of the big data analytics lifecycle. And make sure you also have solid definitions for intelligent data analysis, IDA, and the conceptual requirements of big data architecture.
We've covered the definition, the characteristics driving the complexity, the specialized infrastructure, and that systematic process. This framework should really provide the structure you need.
To quickly summarize and reinforce the material, first, big data is defined by the 5 Vs: volume, velocity, variety, veracity, and value. Second, handling big data requires a shift to specialized distributed architecture and platforms, moving the compute to the data. Third, the conventional versus big data comparison shows that fundamental difference between static, structured systems and massive, dynamic, multi-structured systems. Fourth, analytics follows the systematic steps of the big data analytics lifecycle, running from problem definition all the way to operational deployment. And finally, the goal is achieved through intelligent data analysis using advanced computational methods to find hidden high-dimensionality patterns efficiently.
You know, that brings us to one final thought for you to carry forward into your studies. We spent a good amount of time on veracity, the trustworthiness of the data. If every major system, from traffic light control to industrial process optimization, increasingly relies on big data, how do we, as responsible engineers, ensure the truthfulness of that source data before we build critical systems on it? Think about which steps in that lifecycle are explicitly dedicated to mitigating technical errors, filtering faulty sensors, and ensuring the fidelity of the inputs.
A truly challenging and essential question for the future engineer.
That commitment to data quality is the difference between a functional system and a costly failure. Thank you for joining us for this deep dive into the foundations of big data. And we hope this gave you the clarity and the conceptual depth you need to succeed. We'll catch you next time.